Hello everyone, welcome to Maths Logic. So in the video series of a previous series question of CSIR-UGC net, we have already solved. We are solving the question of quantum mechanics. So we have already solved 6 topics. Okay. Now the next topic is Schrödinger equation, in which we have already solved 4 questions. Now let's move to the 5th question. So this question were asked in September 2022. This was during the COVID, just after the COVID. Okay. So the question is the momentum space representation of a Schrödinger equation. So earlier we have already solved few questions based on the Schrödinger equation in the position space. Now the Schrödinger equation here given in the momentum space. Okay. So the momentum space representation of Schrödinger equation of a particle in a potential VR. VR is the potential is p square plus beta delta p square to the whole square psi pt is equal to I square del upon del t psi pt. This is the energy part. Okay, where delta pi is delta upon delta pi and beta is the constant. So the potential is. So what we have to do is we have to find the potential in a real space. And here we have given the Schrödinger equation in momentum space. So let's write this solution. Okay. So what we have given is p mod square plus beta delta p square to the square psi pt, okay, is equal to I h cut del upon del t psi pt. Now let's compare this Hamiltonian and break it in the potential energy and kinetic energy part. So the Hamiltonian in the momentum space is p mod square plus beta delta p square to the whole square. So the Hamiltonian is written in the terms of kinetic energy plus potential energy. So the kinetic energy is represented here by p mod square and potential energy is given by beta delta p square to whole square. So what we have to find? We have to find the potential energy. Okay, potential of the particle in the potential which is given by VR. So we have to find the potential in the position space, but the Hamiltonian is given in the momentum space. So let's write here we have to do the mapping of this potential in the real space, means the position space. So let's do mapping of the delta first. Let's do mapping of the delta p. So in the position space, we write position as x, and in momentum space same position is represented by I h cut del upon del p. Okay. So what would be the x square? This will be I minus I h cut del 2 upon del p square. And what would be the position in the terms of r? It has component of x, y and z. So what would it be? So it will be minus this is h cut square minus h cut square del 2. This can be written. This can be written by delta p. Okay. Now this is x r square. Now what we will do? We will map directly map the potential energy in which is already given in the momentum space to the potential energy in real space. So we have r square is equal to minus h cut square delta p, and we have the potential energy beta delta p square to the whole square in the momentum space. So this can be mapped in the, this is in the momentum space. And in the position space, what we will write here? So let's write beta first. Then how we can write the delta p? Delta p would be r square upon minus h cut square. Okay, 2 whole square. Okay, so the potential in momentum space is given, which is the function of r, can be given as is something like beta upon h cut square to the r to the power 4. So Vr is directly proportional to r to the power 4, some constant beta to the power h cut square. We don't know the value of beta, and here and the option doesn't have h cut. I think option doesn't have h cut. Let me see first. Doesn't have h cut part. So we will find the proportionality, that whether potential is dependent on r to the power 4, and whether the options are given in r to the power 4 or not. Okay, so here potential is directly proportional to r to the power 4. Let's see, is there any option which has proportionality r to the power 4? Here the proportionality is in the form of exponential. This is not the answer. This is also in the form of exponential. Here the proportionality is r square. So this is not the solution. But look at this, V naught r upon 8 to whole to the power 4. So here the proportionality is r to the power 4. So this is the solution. We have to choose the solution which we have given here from what we are getting as a proportionality. So other the constant part there, which is beta upon I think h cut to the power 4, will be V naught upon a to the power 4. Okay. So we have solved the question for number 5. Now in next video we will solve question number 6 and 7. So thank you till now, and let's meet in the next video.